Hi student and audience. Before starting the lecture, I have several comments to make. First, this is the previous lecture slide and I made one stupid mistake. This is the current sensing network, this is current transformer, and this is sensing the switch current, and it generates lamp signal, and those two signals are added together here and compared with this one to generate pulse width modulator switch driver signal. And this is a converter, but I forgot to place the inductor here. Okay, so without inductor, it's not a converter. Okay, if I develop a buck converter without using inverter, I'll be very famous and I'll be very rich. That is impossible. So inductor is here, then this is buck converter, and this switch current is sensed by this current sensing network for the PWM signal generation in cooperation with this current mode control, and output voltage is sensed and it is converted this control waveforms here. Okay, all right. And in several lecture slides, this one, I made some mistake. Okay, I got confused when referring to the waveforms. So maybe I called with a bad name for some waveforms. Okay, I hope the student and the audience, they can understand what I really mean. Okay, sometimes I made a mistake in calling their label. All right, and somehow the audio quality of this video sometimes becomes worse than normal. I don't know where that comes from. Okay, in particular, over the several pages, I found the audio was not so good as the previous case. Okay, so I don't know how to fix it. All right, so this is about the previous lecture slide, and we move to lecture number 3 on this topic. So title of this lecture is Classical Analysis and Design of Peak Current Mode Control. Okay, so first I'll explain what is classical and what is new in analysis and design of this current mode control. Okay, I think I already said this several times, but in this lecture, I'll redefine about the term of classical analysis and design versus new analysis and design. And basically, we'll go through the small signal block diagram representation of current mode controlled PWM converter not using for classical analysis and design. Okay, that is the content of this lecture number 3. Okay, this is the circuit diagram of peak current mode controlled PWM converter. So here is the PWM switch. Okay, and with this connection, it becomes buck converter. With different connection, it becomes boost and buck boost converter. So this will be the general structure of current mode controlled buck converter. Okay, so it really doesn't matter for this case. This if you assume this kind of connection, it is buck converter, and this is the switch current. Okay, so switch current is sensed through this current sensing network, and the resulting signal Vi, it derived from IC, which is IL for the case of buck converter, is converted to Vi and mixed with this lamp signal. V lamp and SE represent the slope of lamp signal, and it is connected to negative terminal of this PWM modulator, and output is connected to this voltage feedback circuit, and it is going to the positive terminal of PWM modulator, and it is labeled as Vcon, means control voltage. Okay, so nothing is new here. Okay, and this is the small signal version of this. This is the circuit diagram, and this is the small signal model of previous slide. Okay, the difference is just we replaced this PWM switch with PWM switch model, and we introduced two different disturbance here and here. Okay, and this is the gain of current sensing network RI. If you use the current sensing network we studied before, or I fixed some error in the beginning of this class, that gain is 1 over N. N is the turns ratio of current sensing transformer, and R sense is the resistance, okay, employed to the sense inductor current, and that is changed to the voltage here, VI hat. Everything is small signal, so we are using the notation of the hat, okay, and this our voltage is fed to this voltage feedback compensation. Transfer function of that is very simple. FVS is G2S divided by G1S, shown here, okay. And this negative sign indicates there is a negative feedback embedded in this configuration, okay. So there is a negative feedback here, one negative feedback here, and another negative feedback is here, okay. So you should have this, because we are always employing the negative feedback, not positive feedback. And the term classical analysis is this one. In this classical analysis and the design, we assume the sampling effect is very small, negligible, okay. I briefly introduced the sampling effect of the current mode control or sampling effect of the PWM modulator. At that time, I said for the voltage mode control, that effect is very small and can be ignored. And current mode control, you should consider the sampling effect. Every details about the sampling effect will be discussed later. But somehow in the past, they ignored this sampling effect even with the current mode control. Okay, that approach was used for a long time. Okay, before 1980, 1990, something like that. Okay, and that analysis, I call it classical analysis. And the analysis after that, there is just some special event in between, and after that, analysis is called due analysis and design of current mode control. Okay, so this classical analysis indicate this sampling effect is totally ignored. Even you are considering it, you are not considering it, or you are not even mentioning it. Okay, just to forget about control, the sampling effect of current mode control. Then you have the classical analysis and the design. Okay, so this is classical model for the classical analysis and the design of current mode control for 3 different PWM converters. Okay, so from here, this feedback is derived from inductor current. Actually, feedback is derived from the switch current, but you are assuming the feedback is derived from inductor current. This simplifies the analysis without changing anything. I explained that the switching current sensing is functionally identical to the inductor current sensing, because the switching action is performed or once switching action is done, this transition occurs at this point, at the peak point of, oh boy, let me use this, okay. This is IL, and this is IQ, okay. And the switching action occurs at this point. So for this purpose, this IL and IQ are exactly the same. Of course, there is a IL is missing in here. IQ is simply on time version of IL, but for the control purpose, we are using this information. So theoretically, switching current sensing is exactly identical to the inductor current sensing. So you can use either this one, switch current sensing drawing or inductor current sensing drawing. For some reason, this is convenient for this small signal analysis. Okay. So feedback path is derived from the inductor current IL rather than switch current. Actually, we are sensing the switch current, but this is used for the analysis purpose, only for the small signal analysis purpose. This is more convenient than switch current sensing. Okay. And RI is current sensing network gain, and the voltage feedback compensation is simply G2S divided by G1S. So you have negative sign here, This indicates the negative feedback. All right. And the modulator gain, we used FM prime. The reason for this is FM was PWM gain for the voltage mode control. Okay. Modulator gain for the current mode control is different from the modulator gain of voltage mode control. So to distinguish between two different expressions, you are using this prime. So FM prime is modulator gain for the voltage mode control, and which is different from the modulator gain or PWM gain of voltage mode control. Okay. And this slide is about the modulator gain FM prime. For the voltage mode control, FM was very easy. FM was this one, 1 over VM. VM is peak value of ramp signal. So this is VM, and this is TS. This is switching period TS. So VM is TS times slope of this ramp signal. So this is the case for the voltage mode control. But current mode control expression is this one. Okay. So FM prime is 2 divided by SN minus SF plus 2 times SC, parenthesis, multiplied by TS. This is different. Derivation of this is not so easy, but it is feasible. You can derive this, but you don't have to derive this by yourself. I already derived it. And this guy is Fred C.D. I said this, he is the second father of power electronics, and he derived this, okay, and I copied his result in chapter 8, example 8.3 in text, okay. You know what text is, okay, textbook of this lecture, that the proof is done here. So we assume this is correct in some sense. Okay, in some sense means there are many different versions of this expression, but I like this one best. I think this is the most accurate one. Okay, there is a good reason for that. Okay, first, it has this SN slope of this on-time inductor current, sensed inductor slope of sensed inductor current, not the inductor current itself. Inductor current times current sensing network gain. Slope of that is appearing here, and this is uptime. This is SN, and this is SF. It's not shown here in the switch current, but we have the slope. Okay, so VI is IL times current sensing network gain, and this is 2 times this is slope of V lamp. This is called the stabilizing lamp and the compensation lamp. Okay, because the original purpose of this is to stabilize this current mode control to avoid the subharmonic oscillation. Okay, right. This is a very good one. There are many different ones. We will discuss that later. And one interesting thing is when SN, SC equals 0. Okay. Oh no. SN, SF. I'm sorry. This should be SF. They are 0. That means there is no current feedback. Okay. Only SE is existing, then that is what? That is voltage mode control. For the case of voltage mode control, you just put SN, SF0, then this cancels, and this is this one, VM, and FM prime becomes FM. This is a case of voltage mode control. So one advantage of this expression is it makes sense when this becomes 0. This current mode control is removed. It reduces the modulator gain of voltage mode control. Okay. All right. Okay. And another one is this one. Assume S E is 0. That means what? There is no this compensation lamp. Okay. Then you have three different cases. D is smaller than 0.5, larger than 0.5. This case is the D is exactly 0.5. Consider three different cases. For this case, this slope Sn is larger than Sn. I'm talking about the magnitude. The increasing slope of inductor current is steeper than decreasing slope. So for this case, Sn is larger than Sf, and Se is 0 because Se is set up 0. Okay, this is a current mode control without stabilizing lamp. When D is less than 0.5, Sn is larger than S5 always. That means this becomes positive number. So this is stable. Okay, because we are using the negative feedback, this is stable. Okay, when this is D is 0.5, then this on-time slope and off-time slope becomes the same. And we'll explain this case later. First, consider this one. If D is larger than 0.5, that means increasing slope is less steeper than decreasing slope. Namely, this SF is larger than Sn. Then this number becomes negative. Then means what? You have positive feedback. System is unstable. Okay. So this indicates the condition of the subharmonic oscillation with different value of the T, and the borderline is D equals 0.5. And this is a case when D is 0.5, then waveform is shown here. Consider this is the original waveform. Okay. Then this slope should be the same, regardless of the type of converter. Okay. So this slope and this slope is the same. Then this becomes infinity. Fm prime becomes infinity. This is the condition to generate the sinusoidal oscillation in linear circuit. But this is another linear circuit. So this is a case with inductor current waveforms with this condition. There is no external lamp and the Dewey ratio is 0.5. The steady state waveform is this one. Okay. So some disturbance is introduced here. Then this will increase and it hit this value and this will decrease. Okay. This slope and this slope should be the same to make output voltage regulate at the fixed value. Okay. To have the same out value, Dewey ratio must remain the same. So in here, Dewey ratio is 0.5. Then in here, Dewey ratio should be the 0.5. Also, for that purpose, this control voltage should increase like this. Okay. So here we are considering the closed regulation. So on the condition, the output voltage is regulated at a fixed value, then control voltage should be increased like this. Okay. Then this is the initial error. Error is between this original inductor current minus this part of the inductor current, which is shown as del ILK. It's the same as the del ILK plus 1. Okay. Error is not increasing or decreasing. It remains the same. That is the same as the oscillation. Sinusoidal oscillation with constant amplitude. Okay. So this is the nonlinear system, but similar phenomena is occurring here with Dewey ratio of 0.5 without external lamp. Okay. So this is expression. It contains the information about this voltage mode control and this subharmonic oscillation, which occurs when Dewey ratio exceeds 0.5. Okay. So it contains the very informative information. Okay. And Why I'm saying this? There are many different expression of this Fm prime. Okay, so this is one we went through, and this is proposed this FCD, the second father of power electronics, and reconfirmed with this guy D10, Dong10, a Chinese guy. Okay, he derived the same expression, effectively same expression, and he analyzed the sampling effect of color mode control. If we ignore that term, then that is the DC gain, constant gain, is exactly same as his expression. Okay? There is another expression. This is developed by Richard David Middlebrook, the first father of power electronics. I don't know his name. I don't know how to pronounce his name. Okay, some guy. Together, they proposed this expression, and another guy, I know his name, but I don't know how to pronounce his name, proposed this. I know this guy very well, Raymond Ridley. He proposed this. Okay, why many people propose different expression of this? I don't know. If you take a look at his paper, this looks correct. If you take his paper, this looks correct. Okay, so all of them can be considered correct, and they claimed mine is the correct one, and others are some false. Okay, but I don't think so. I think this is the best one. Okay, I'm not interested in figuring out the exact one. Okay, there is some tricky in analyzing this sampling effect. Okay, so I wrote one paper comparing these things. Comparison is meaningless. I'll explain that later. Okay, but this one matches with this one best matches with the circuit operation of this scheme. So this is I think this is the best one. Okay, and another thing is this one. Consider this one. We have 4 different expressions, and consider this is a 0.5. Then this becomes 0, and this becomes SE times TS. It's the same as this one. So Fm prime 1, Fm prime 4, they are same. Okay, and the magnitude of other expressions are smaller than this. Okay, if you think about this, so this is the smallest, and this one is smaller than these two when this special case. Okay, so this is not a general analysis. Okay, it's meaningless to have the general analysis on this. So just typically knowing this is enough. Then I wrote down this is the most conservative selection. Conservative means safe selection. Okay, assume this is some number. Then this number is smaller than this. This number is smaller than this. Okay, smaller is safer. Okay, smaller. If you go to the smaller direction, there is more conservative design, which is safe. Okay, if you go the other direction, that becomes more dangerous design. Okay, if you use this one, then actually this one is correct, and you are in trouble. Okay, if this one is correct, but you are using this, at least you are safe. Okay, so larger value of this can cause problem. So using the largest case is the safest one. Okay, so this is the good in that sense too. And another the more important thing is I already explained this. This can predict the oscillation of this one, subharmonic oscillation without the stabilizing lamp, and the Dewey ratio is 0.5. It generates the negative sign. So it becomes positive feedback, and the system becomes unstable, right? And more important thing is you rearrange this. Okay, this is the same expression, and I moved this SE in this side and put everything else in right hand side. Then you have this. Okay, and this expression is very familiar too. This is what? This is the condition for the lower limit of external lamp with the duty ratio larger than 0.5. Okay, so we are assuming there is the lamp, okay, and the minimum lamp is this one, and because this is the positive number, actual lamp slope is obviously larger than this. Okay, with this you cannot have subharmonic oscillation regardless of value of your steady-state duty ratio. That makes sense? Okay, so there are many things which coincide with the physical operation of this circuit, and that kind of phenomena, that kind of explanation is not possible with this. Okay, so this one is the most reasonable one. Okay, so I'm using this all the time, and I think this is the most correct one. Okay, I don't know the exact sense. Maybe this guy, they will be upset hearing this. Okay, but they don't have this kind of features in their expression, right? Okay, this is very important. So this is the most conservative selection of FM. Okay, when you are designing the current mode control, you should determine this FM. Okay, prime, right? Okay, so you are using this. The reasons I already explained. So this is derived by Fred C.D. He has some additional term here that represent the sampling effect of the current mode control, but somehow he ignored all of this, and he ignored the sampling effect, and he are using only this one. That is fine in some sense. Okay, so you know everything. So SN is on time inductor current, sense the inductor current slope. So for the buck converter, on time slope is Vs minus Vo divided by inductance L times Ri. This is a boost converter, buck boost converter, and uptime slope is this one. This is positive, but this is a boost converter. The slope, magnitude of slope, without this sign, it becomes negative. So to make positive, I place this. This is a negative, so I need this. Okay? So this is very simple. All right. This is the schematic conceptual diagram of this control. Okay. So I have a switch here. Some absurd switch. If switch is connected, that is what? Current mode control. Okay. This is active and switch is connected to this type, then that is what? That is voltage mode control. Okay. If you design a converter and you put switch here, this turning to this counterclockwise direction makes current mode control, and the other way is voltage mode control. Okay. So when you are writing paper about the comparison between voltage mode control and the current mode control for 3 different converters, you can use only this one diagram. Okay. Then that can be represented 6 different configurations. 3 from power stage, 2 from control scheme. Okay, so this is the very convenient way of representing PWM converters. And the small signal block diagram. First, forget about this. Forget about these boxes with blue curve, lines with blue curve. So you have only black ones. This is the input to output transfer function, open loop transfer function, input to output, load current to output, open loop transfer function. This is a duty ratio to output transfer function. Okay? And for the voltage mode control, there is a voltage feedback compensation FV here, and it's coming here. And for the voltage mode control, FM, well, this was FM. We are talking about current mode control. So FM is changed to FM prime, and we have feedback from the inductor current. And the inductor current is affected by this duty ratio, and the inductor current is also affected by this input voltage disturbance, and it is also affected by this load current. So we are copying this here, and output of this was VO hat, and the output of this is IL hat, which is inductor current, small signal inductor current, maybe sinusoidal small signal variation of inductor current. and there is a current sensing network here. This is the gain of current sensing network, and they are added. This output of this voltage feedback circuit was V-con, and it is added, but actually subtract. Okay, actually subtracted. Then it goes here. Subtraction comes from this. Okay, we are adding, but this terminal is you have minus sign here. Okay, so this is added, but actually it's subtracted. Okay, so you have this signal here. So you have this and this. This is negative feedback from the inductor current, and this is the negative feedback from our voltage. Okay, this is called the two-loop control. There is two feedback loops. One is here, another one is here. Some people call it this is the inner loop. This is the outer loop. That makes sense. Okay, or some people say this is a current loop and this is a voltage loop. That also makes sense. Okay, so this is the extension of our previous small signal block diagram of voltage mode control to current mode control by adding 3 additional functional blocks and adding this one and modifying this. Okay, so modulator gain, you are using the FEV-CD expression, and the current sensing network gain, RI, is this one. If we use the previous current sensing network, if we use one resistor here, then get that value of the resistor is current sensing network gain, RI. Okay, so whenever we are using this, we are talking about the previous current sensing network. Okay, then here I copied this. Okay, there are 6 transfer functions. Okay, and all of this can be derived from the small signal model of power stage. Okay, using the small signal model, you derived this input remain the same, and input you have 3 different input, and output is this one. In here, the input remain the same, but output becomes IL. Okay, this is very easy because this is the power state model is linear time invariant model. Extremely simple circuit analysis will provide expression of this. Okay, this is the general expression: KVS, KVD, KIS, KQ, KP, KID. Okay, KVS is constant in input to output transfer function, something like that. Okay, and we have expression for this: KVS, KVD, KIS. This one will be varied with different configuration of power stage circuit. Okay, so this is the expression of these variables for the buck converter and the boost converter and the buck boost converter. Okay, all right. Why I shade this? The reason for this is previously we were dealing with only 3 transfer function blocks in voltage mode control, and we need 3 more for the current mode control case. Okay, so this is the newly derived transfer function. Derivation is almost the same as this one, easier than this one some case. Okay, and expression of this blue shaped transfer functions are shown here. Okay, so KID for buck converter, KID for boost converter, buck boost converter, so on. So every information is here. Okay, so deriving the power stage transfer function is very easy. Okay, you don't have to repeat this. So you have a table. So look up this table whenever necessary. Don't try to memorize this. Okay, deriving this is nothing. So we have a table here. Okay, one important caution is for this R is coming from resistor. Okay, so this resistor is load resistor. Okay, but there are another resistor here, resistive parameter. Okay, that resistive parameter is sometimes this resistor is defined as VO divided by IO. Okay, so this is different. Okay, this can be defined for the inductive load. Okay, something else. So this is true for the resistive load. There is no distinction between R and this one when the load is actually a load resistor. Okay? But if the converter is connected to something else, something other than resistive load, okay? I said there are few people or there is no people connecting the resistor at the output of a converter. Okay? That is very stupid. Maybe something else, maybe the other converter or some equipment, some device, some apparatus is coming as the load, then this should be replaced with impedance, GLS, and it should be differentiated with this R. Sometimes there are two R here. Maybe for the boost converter, I don't know. This R and the other R can be different. One is R, load resistor, okay? This quantity defined in this manner. The other one is load resistor, resistant of load resistor. They should be replaced with GLS, okay, for the general load, okay? But you don't have to distinguish between them now. So you assume your converter is connected to the load resistor, then you can use this expression, okay? All right, so this is the end of this lecture. And in this lecture, we discussed the definition of classical analysis and the design, and this functional diagram shown here. Okay, this one, and we went through some details about this modulator gain, FM prime, this one. This is the best choice, and I introduced 4 different ones, additional 3 different ones, and this is the expression for the SN and SF, and this is a general diagram, circuit diagram, which represents 6 different converter with different control scheme, and this is the block diagram representation, and inside of block diagrams is summarized in this table here, and finally, later on, at the end of this study, okay, then you need to differentiate between R and this one, VO divided by IO. If the load is purely resistive load, they are the same, but some in practical case, they are always different. Okay, always different, but you don't have to worry about this. Okay, all right. This is the end of this lecture 3. Okay.